All right. Before the break, what we did, we saw that you can actually, in integrated circuit biasing techniques, you can take a reference bias, a good reference, and replicate it multiple times. And you can you can basically copy that. You saw that we can actually make different variations of that with higher output impedance, lower output impedance, etc., etc. You can have ones that can source current, you can have ones that sink current, and all those things. So we can actually, if we have one good reference, we can replicate it multiple times with good output properties and things of that sort. There are lots of techniques to play with that. Now, the key question, one of the key questions that arises at this point is that, well, how about that reference branch? How do we generate that? Well, the simplest form of that reference branch is just a resistor, if you think about it. Right? So if you have something like this, let's say for the sake of argument, in a bipolar transistor, you have something like this, and then, of course, if I ask you what is this Iref, well, Iref is going to be VCC minus VBE on divided by R. Now, you can see that this is clearly not supply independent, right? Because supply plays a direct role. If your power supply changes, this current changes. You can imagine that this is not going to be particularly temperature independent, because you have resistors here and VBE-ons, and we haven't done anything in particular to make sure that it's temperature independent. So Murphy's law says that it's probably going to be temperature dependent. And then also, you haven't done anything to make it process independent. The process variations in R and things of that sort can result in variations. We haven't talked about what's happening inside VBE on, how it behaves. But again, the variations in that can also introduce problems. So the question is, how do we make this? Make something that's better than this, something that's a little bit more stable. So now we can think about it in both contexts of MOSFETs and bipolars and all those things. So let's start with the MOSFETs and see if there's anything in the MOSFET, starting with making the temperature, supply voltage independent. Is there something in MOSFETs that allows you to make it relatively independent of the supply voltage? You want to make a current source whose value depends, to first order, on a voltage that's not the supply voltage, right? So what voltage is there that's not supply voltage when you're dealing with MOSFETs, for example? What are the voltages that are out there? Is there some voltage that doesn't change with the power supply? Ground. Well, ground is 0. Yeah, that's fine. But ground doesn't change with power supply, but it's 0 by definition. So you need a non-zero voltage, preferably. Yes. The threshold voltage, right, exactly. And you want to say the same thing? OK, threshold voltage. Yeah. The threshold voltage of the MOSFET, right, itself doesn't depend on the power supply. For example, we don't know how it depends on temperature. Well, I'll tell you what it does. Typically, it's like around -2 millivolts per degree C. So it has a negative temperature coefficient. But starting with the supply, let's start with the supply and see what we can do. So what we need is somehow to take this VT and drop it across a resistor to generate a current, right? How can we take this VT and drop it across a resistor? Where do you see the VT? Well, you see the VT across, for example, where? You see it across the gate source of a MOSFET. So would it make sense to put the resistor here and say, OK, well, this is the resistor. So the current through this resistor is VT because this is VT plus delta VGS, really. But let's say delta VGS is small, or we can make it small. Can we do this? Would this work? Would there be current flowing through this resistor? Because this current has to come through the gate, right? So what happens if I actually do just this? If you actually did this, what would happen? Yeah, the transistor will turn off because this gate is shorted to ground through this resistor. So eventually it will discharge to ground. You will go below VT unless you have if you have a depletion mode MOSFET, it will still be on. But if it's an enhancement mode MOSFET, in other words, if VT is positive, it's going to turn off. So nothing's going to happen. So this by itself doesn't work. But it doesn't mean that we can make a modification to this to make it work. So what is the problem here? The problem is that there's no current flowing. There's no pathway for current to flow because whatever current right now has to flow through the gate, right? Which it can't, right? At least based on the simple model. So we have to create a means for this current to be provided here. And also some sort of a current to be provided for the MOSFET to maintain operation. How do we do that? Well, what if I use a current mirror? It has to be the complementary one. It has to be PFET. And if you use a current mirror like this, let's say this is a good current mirror, it will force these two currents to be equal, right? So whatever current is going through your MOSFET will be forced through your resistor. And as a result, it would produce a voltage here that would maintain a VGS minus VT. And in principle, this is not a bad idea, right? So let's say if it worked, and there's a little problem with this which we'll need to fix later. So it doesn't work in its current form, and I'll tell you why in a second. But let's say if it did, what would be what would be this current, I, this I? I would be VG, do you agree that it would be VT plus delta VGS divided by R, because that's that voltage. That's the current that will be maintained. Now, if I wanted to make it mostly dependent on VGS, I'm sorry, on VT, what do I need to do to make my delta VGS small? I know my we know delta VGS is square root of ID over mu n Cox over 2W over L. So can you propose a simple way to make this delta VGS relatively small compared to VT? I want the impact of this term to be small compared to that term. Right? W over L, make it large. If you make your W over L large, this becomes relatively small, so you can make this, so W over L going to infinity, this becomes roughly VT over R. So you get a current, in principle, that is proportional to the threshold voltage divided by the resistor. Now, is this a good thing from a, so from a supply voltage independence, is it a good thing? Yes, there's no supply voltage in this expression, right? So it doesn't depend. If you have a 5 volt supply or 6 volt supply, it will generate pretty much the same current. Is it good from a process independence perspective? Well, not quite, because VT is determined by, for example, the implantation charge that you put, the threshold voltage, you remember, you adjust it with the implantation. There are a lot of other parameters in there in the VT and all those things. So it has a lot of dependence on parameters of the process and variations, so that can change. How about temperature? Well, I just told you that this has a negative temperature coefficient, and a standard resistor, or a regular resistor, let's say, will have a positive temperature coefficient. So is that a good thing? Ratio of a negative to a positive is not a good, because it becomes more negative, right? The denominator becomes smaller, the numerator becomes smaller, the denominator becomes larger with temperature. So that ratio doesn't stay constant. So it's good from a temperature, from a supply perspective, but it's not very good from the temperature or supply perspective, power supply. They call them PVT, power supply, process, voltage, and temperature, PVT, process variations, voltage variations, and temperature variations. So, okay, but there's another problem with this, which we haven't really gotten into yet, which is that if you look at the sign of the feedback in this thing, so if this node goes up a little bit, right, from here to there, what kind of stage do I have? I have an amplifier, right? What kind of an amplifier is this, if this is the input and that's the output? It's a common source, right? So it's an inverting amplifier. And this node is shorter to that node, so it's the same node. But then this is another inverting amplifier. This is another common source, right? Which basically inverts it one more time, and then you come back and phase. So this can actually, in principle, be a positive feedback network, which can result in some poor behavior. So we have to kind of break this feedback loop. So one of the things you could do, the way, if you wanted to normally do this, is one of the ways is to basically put another transistor here to create that isolation. And what you do by doing that is that you can see that now the loop within this pathway has a negative feedback. And again, we haven't gotten into feedback in details. We'll get into it later. But you can see that now this is a follower. So this goes down, this pushes down. So now the feedback sign is negative, because if this goes up, it's being pushed back down. But other than that, this is one way to generate a threshold voltage reference, right? It has another problem. The problem right now is that it's basically not dropping the, there's a delta VGS, so it's an approximation. Now, in general, there's a lot of these scenarios that you will see when you're talking about these supply voltage independent, PVT independent generations. You're trying to drop a voltage or the difference of two voltages across a resistor and turn that into a current. And we'll see more examples of that as we go. Now, the key question is that are there good ways to achieve this? And one of the things that we do here, obviously, you saw one of the themes, and this is an important thing to look at, is that you use a current mirror to force the currents of the two branches to be equal, right? So we can have two branches to ground whose currents we can force to be equal. But also what we are trying to do often is that we are trying to get the voltages to be equal too. So you want to create two branches whose currents are the same and they share the same voltage. Equality of the current is forced by the current mirror, right? So you can always have a current mirror. And then if you want to make it a better current mirror, you can make it cascade or something like that. But again, this is a current mirror. So basically this current mirror, if it's working properly, it forces these two currents to be equal. Right? Now, we want something else. We want to have also something that allows two branches connected to ground to share the same voltage. So we want V1 and V2 to be equal too. So we want to make V1 and V2 equal, and we want I1 and I2 to be equal. I1 and I2 equality is dictated by this current mirror. So the question is that, can you think of something we can put in between, in here, that would allow us to force these two voltages to be equal? So think about it this way. If you can make these two voltages depend or be derivatives of, derivative meaning derived from, not the calculus derivative, of another voltage, if they're generated off of a different voltage, if they have a fixed relationship with a given third voltage, then you can force them to be equal, right? Let's say they are both lower than that voltage by 1 volt. If I say I have a third voltage, and these two are all both 1 volt below that voltage, then they would be forced to be equal, right? Can you think of a simple way of using transistors to achieve that? Well, this is one way. So let's say they are both sharing the same voltage, right? We'll talk about how to get where to connect this voltage in a second. But let's say this was connected to some voltage, some V1. Oh, well, we use V1, V3, right? If it's V3, do you agree that these two transistors, if they have the same size and they are forced to have the same current, will have the same VGS? The first order? So these two voltages have to be equal, because they are both VGS below V3. So you can force these two branches to have the same voltage and the same current. This is what I call the entire system. I call a floating mirror, because it allows these two terminals to be floating with respect to the other ones. So it's basically, and this is what I call it, isolator or a floater with respect to that. This becomes a floating mirror. Now, we need to do something about this gate, right? This gate needs to be connected somewhere. It can't be just left floating, really. So where can I connect it? I can connect it to one of these two sides, this side or that side. Which side would you connect it to? Would you connect it to the left side or the right side? And why? So here's one thing to think about. This is VCC or VDD, and this is ground, right? You don't want to create a situation that the pathway between VDD and ground is defined by a bunch of diode-connected devices, right? Because what happens then is that you will draw current directly through that, right? It's like having like 3 diodes between the supply and ground, or 2 diodes on a resistor. So there's one side that if I put this on, it would create that kind of pathway. And there's another side that it doesn't. Do you agree that if I were to put this diode connected here, I will have a diode connected here, and whatever I have here? So whatever voltage I apply would appear across 2 diode connectors and whatever I put here. So that would dictate the current. There's no flotation. There's no separation. There's no isolation. For isolation to happen, you need to have at least one side to be high impedance. And that's why you put it on this side. Because you have a high impedance here and a low impedance up there, and a high impedance there and a low impedance there. So if you have one side that's high impedance, that side can play freely. It can be open. It can float. It can follow the other side. If you put 2 low impedances to one place, then you have 2 things that are fighting each other strongly. One way to think about high impedances and low impedances, high impedances are like loose springs. And low impedances are like stiff springs. Right? If you want to have something that can have play, you need to have at least one side of it attached to a loose spring. If you attach 2 stiff springs to each other, right, then you can't move much around. One side has to have give, at least. That's one thing. And that's what high impedances are. It's give. So this way, you create this thing. So this is what we call a floating mirror. It's a mirror, but it's also does more than just a mirror. It just forces these 2 voltages to be equal. So now, if you use something like this, can we take advantage of, can we redo what we did with the threshold voltage and see if we can make that? So how do I make the threshold voltage? Well, the easiest thing is to put a diode-connected device here. Can I do that? Sure, because I don't have any, yes, this is diode connected here, but then it's defined this way with a high impedance. And there's a high impedance here, so this middle part can move up and down in voltage with respect to the other part without having to worry about it. And then you want to drop it across a resistor. So if you do just this, what do we get across the resistor? Well, we get the same expression, right? Because now the voltage here is Vt plus delta VGS divided by R, would define the current. So we achieve the same thing. Now, but this time we may be able to actually play some of our tricks to get rid of that delta VGS. How can we do that? Think about it here. If this is Vt plus delta VGS, right, what is this voltage? If you go 2 VTs plus 2 delta VGS, right? And then you drop down, you get to Vt plus delta VGS. And that's why you have Vt plus delta VGS across the resistor to produce the current. That's where that Vt plus delta. Now, what are we trying to do? Ideally, we are trying to get rid of this, right? We are trying to get rid of this delta VGS. Do you agree? Can you think of a W over L trick that would allow you to get rid of it? You want to drop what here?
Yeah, cut the middle to W over 4.
Right, because you are trying to drop a Vt plus 2 delta VGS here. And to get Vt plus 2 delta VGS across here, you can cut this by a factor of 4. And what that does, it makes this drop across here, Vt plus 2 delta VGS, which basically makes this go away. And this makes this exactly Vt over R. So you get rid of that delta VGS overdrive systematically, not by just making W over L huge. Make sense? Does that concept make sense to you? I mean, you can apply it. You can see that we've applied this trick twice already, right? And these kind of tricks are useful tricks if you understand what you're doing with them. So that's fine. So that's one way to generate something that's independent of the supply, at least. And now you may say, okay, well, what do I do with this? You have this thing. Let's say we made this thing. It's VT over R. How do we use this? How do we make our reference current? Well, this is our reference current, right? Because I can replicate it one more time here, and I can feed it into my distribution branch of my current mirror and current generation network. And whenever I need to use it, I can use multiple copies with different W over Ls or different sizes, and I can replicate that copy. So this whole thing becomes that IREF that we used in the current mirror discussion. Does it make sense? So when you see something like that, you have to be able to break it down. You can say, okay, well, what is this part doing? What is this part? These are Legos, right? Different kinds of building blocks that you're putting together. And if you understand what they individually do, you can put them together and make different things. All right, so that's for that. So let's say, okay, VT is fine, but let's say we want to find something that has better properties, temperature-wise and supply voltage-wise and all those things. What else is there? Well, let's go back to the BJTs. Is there something we can use in the BJTs? Do we have a voltage there that's kind of useful or potentially useful? Well, we have the VBE on, right? We can do exactly the same thing that we did with the MOSFET with the VBE on. In fact, all you need to do is just to replace this with a diode-connected device. And what that does, it just makes this a VBE on over R. So you can make a VBE reference, right? The question is that what is the temperature dependence of the VBE? And that's an interesting question because it actually can be a little bit of misleading question in the beginning. So what you have, so the question is that what is the temperature dependence of VBE? So you may come back and say, well, VBE is VT natural log of IC over IS. And VT is KT over Q in a bipolar transistor. And this is some natural log, so it appears that there's a temperature here, so it must be proportional to the temperature, right? Wrong, unfortunately. This guy, this IS, has such an incredibly strong temperature dependence that even through a log, it overwhelms. So we need to really understand what the temperature dependence is of this thing. And to do that, we need to really write an expression for the IS. So IS, the saturation current, is Q, the electronic charge, times A, the area of the emitter, which we kind of expected, times Ni squared, which is the intrinsic number of carrier concentration in an undoped situation, times D, which is the diffusion constant, divided by the width of the base and the doping concentration. So that's the expression for IS. Now, there are several things that don't depend on temperature. The electronic charge doesn't depend on temperature, or area of the first order. If you think about, if you ignore the thermal expansions and things of that sort that are very tiny, don't depend on temperature, or the width doesn't depend on temperature, or this doesn't depend. But the things that do depend on temperature are this and that. Well, Ni squared is, in fact, you can actually show, so let me just get the exact expression for it, is T to the 3. So it's some constant. I call it D prime. T to the third e to the negative V band gap over Vt. Now, T is the absolute temperature. This is some proportionality constant. Now, VPG is the band gap voltage of the semiconductor. So in the case of silicon, it's about like 1.1 volts. So that's what the band gap of the band gap voltage of the semiconductor. And it makes sense, right? Because the smaller the band, the larger the band gap is, the smaller the intrinsic would be, because these are thermally generated electron-hole pairs, right? So that dependence makes sense. There is also another relationship, the diffusion constant. D over mu over mobility is KT over Q. And it rhymes. That's how you remember it. D over Q, mu is KT over Q. So basically, D is KT over Q, or KT over Q times mu. And mu has a temperature dependence itself too, the mobility versus temperature. Now, this is also pretty sophisticated. It has two regions. There's a region where it has a slope of 3/2, or power of 3/2. And there's a region where it has a roughly power of negative 3/2. This is around 100 Kelvin-ish. So at temperatures that we are interested in, usually we are in this region. And here, basically, it's an impurity scattering, and this is the lattice scattering. There are two different mechanisms coming in. It goes into device physics, semiconductor physics of it. We are not going to get too deeply into that right now. But bottom line is that in the region of interest, we have this kind of dependence for mu. So we have basically D is, you can plug this in here, and what you get is that you get an IS that is a bunch of parameters here. You get a K. So let's absorb all the non-temperature dependent parameters into some constant E. What you have as temperature dependence is this T to the 3, T to the third, T cubed. You have this T, so that makes it T to the 4. And then you have the dependence on the mu, which is T to the negative 3/2. And then you have that exponential with the band gap. So you combine all of those things, you get roughly E T to the power of, it would be 5/2, right? Yeah, 5/2. E to the negative VBG over VT. And okay, now we plug this back into this guy to see what VBE looks like. So let's do that calculation. So you say VBE, which is VT, or let's say write it as KT over Q, KT over Q, natural log of IC over IS. So what do we get? We get KT over Q, natural log of IC, minus KT over Q, natural log of IS. Now you go to natural log of IS, you get all this stuff. So you get basically KT over Q, natural log of IC, minus, now you calculate the log of this thing, you get KT over Q, natural log of E, minus KT over Q, 5/2 of KT over Q, natural log of T, and then you get the natural log of exponential of E to this, so which basically gives you the VBG, the band gap, the natural log of VT times natural log of that. So what you see here is that you can see the negative temperature coefficient dependence here. And the other interesting thing that you see here is that it's directly related to the band gap voltage. Now, band gap voltage of the semiconductor is an intrinsic property of the semiconductor. So you don't expect it to depend too much on the supply voltage or process variations or even temperature. And that's a good thing. So eventually, our target would be to get to this voltage and use that as a way of making a reference. Okay? So the question is that how do we get there? So first thing we see is that it's a negative temperature coefficient, right? So still it's bad because it's a negative temperature coefficient divided by a positive temperature coefficient here. So it gives you still a negative temperature coefficient, right? It's less process dependent, fine, but still we need to work on that. So how do we do that? Is there something in there, when you look at that expression for example, VBE or something like that, is there something in there that actually has a positive temperature coefficient? It's this guy, right? KT over Q. Question is that, can we come up with a way to generate or extract this KT over Q and use it for generating a reference? Let's call it the VT reference, or it's also sometimes called PTAT, proportional to absolute temperature. PTAT, you may see PTAT. And you may see CTAT, which basically means complementary to absolute temperature, which basically would be like VBE. It goes down with temperature. So how do we extract the VT? Why couldn't we extract it here? Why didn't we get the temperature dependence? Because this guy came to kill us, right? This IS. So we have to somehow get rid of the IS. How do you get rid of the IS in these expressions? You have expressions that look like this. VBE, or KT over Q, natural log of IC over IS. Can you think of a way of getting rid of that is in the log? Do you see a way of getting rid of it?
Add a KT over Q element bias somehow.
Right. So if I want to get rid of something that's multiplicative in a log, what do inside the argument of the log, it's multiplicative. What do I do outside the argument of the log? Add or subtract, right? So what if I subtract two VBEs from each other? What if I could take one VBE and another VBE, and let's say I subtract them from each other. In other words, I force these two voltages to be the same. If I force these two voltages to be the same, and I have a resistor here, the voltage across this resistor, do you agree, would be this VBE minus this VBE? So let's say VBE 1 and VBE 2. And the one way to do it is to make this 1x and make this n times larger. So basically make this out of n transistors in parallel. So its is n times larger. But it's still the same is, just n times larger. Can you think of a way of forcing these two currents to be equal and these two voltages to be equal? Well, we just devised the way, right? We called it the floating mirror. Right? So you can have a current mirror, it can be MOSFET or bipolar. And then you can have the other element, which is the floater or isolator. And what these two do in combination is that they force these two currents to be equal, and they force these two voltages to be equal. Right? Now, if that's the case, what do we get? We have VBE1 equals VBE2 plus R times I, which is this voltage drop. So what I'm saying is that this voltage plus this voltage is equal to that voltage. Right? We force them to be equal by the use of this floating mirror. But we can express these in terms of VTs. Natural log of IC over IS, and this one is VT natural log of IC over NIS, because this is n times greater. N of those transistors, you can put n copies of that transistor. And this is what you get. Now, if I move this to the other side, what happens? You see VT natural log of the ratio of the arguments, right? What's the ratio of this argument to that argument? What is this divided by that? N, right? Both IC and IS cancel. So I becomes VT. Now, this VT is really KT over Q. Let me just write it as KT over QR natural log of N. So now we've actually succeeded in producing a current which is proportional to the absolute temperature. And now, as such, this is probably a better combination, because if this is growing with temperature, this has a positive temperature coefficient. This also has a positive temperature coefficient, so they can actually, to first order, maybe cancel each other out somehow. We'll do better than that, but just that's next step. So, but the key part is that this is also called PTAT, proportional to absolute temperature. Right? So now you have we have two things. We have a VBE which has a negative temperature coefficient, so this is important, right? And it has a band gap part. And we have something that has a positive temperature coefficient. If we add sufficient amount of this to that, it may appear that you may be able to get this thing out. And that's what a band gap reference really is. So you take this PTAT that you generated, and then you copy it somewhere, and then you pass it through a resistor, and then you add it to a VBE. And if you pick this resistor to be the right value, say X times R, this current going through this resistor will introduce what voltage? It would produce a voltage that's this thing, kT over Q. R's cancel, you get times x times natural log of n times x. X is not probably a good symbol. Let's just make it m. Right? So the key is that these two resistors are of the same kind. If they are of the same kind, then they actually would produce, the ratio will cancel out temperature-wise. So what you have left with are ratios. You have the natural log of n, which is the ratio of the size of this guy to that guy. And then you have the m, which is the ratio of this resistor size to this resistor. And that's the voltage. This is the voltage across the resistor, then plus VBE of this transistor. And this way you can actually produce something that's called a band gap reference. And it's very insensitive to the supply voltage and temperature and things of that. So you can actually make this the first order. You can try to cancel these two dependencies by applying the right amount of PTAT to it and adding the right amount of proportional to the negative. So you have something that has a negative temperature coefficient, and you have something, simplest way to think about it. This voltage will have a positive temperature coefficient. This voltage has a negative temperature coefficient. You add them with the right proportions. To first order, you can cancel them at some temperature. Now, this is very, very first order. There are lots of much more sophisticated things that you can do on top of this. And there are people who make a living out of making these things very, very precise and insensitive to these parameters. Now, before we wrap up, I want to say one more thing about this, and then we can just quickly wrap it up. Let's say, why do we care about making these independent of temperature and supply and, process variations? Because we have some design parameters that we want to make independent of those, right? You don't want your circuit to behave differently when it's cold or hot, when the battery is fully charged or when the battery is empty, from one chip to the next one. You want them to all behave the same way. Now, but one of the things that you actually design for is gain, right? So what if we wanted to make something, let's say a simple differential amplifier. Let's say you have a simple differential amplifier. And let's say it's a bipolar differential amplifier. And we wanted to make this independent of temperature. The gain of this to be independent of temperature. So what is the differential gain of this stage? So this is some tail current source. Let's say I tail. What is the gain? What is the differential gain of this thing? We've calculated this before, right? GMRC, right? It's GMRC. Now, what is GM in terms of the parameters? So GM is I tail divided by 2, right? I tail divided by 2 divided by VT times RC. So that is our gain. Right? Now, we want to make this independent of temperature. How should the I tail behave? If I make an I tail that's absolutely independent of temperature, would that be a useful thing for me to bias this thing with? No, because I still have this VT here, and I have the temperature dependence of this resistor. So in fact, if I want to keep the gain constant, I don't want a constant current source. What do we want? Proportional to temperature and inversely proportional to the resistor, right? Do we have such a thing? Have we already created one? So if I bias it with this guy, I would probably get the right results, right? So how do we bias it with this guy? Instead of doing a PTAT, a band gap, I make another reference branch here, right? I tap off of here. I come here and make a current source that way. Now this can be MOSFET or bipolar or something. Well, is this correct? By the way, what I did is correct, or is it completely bonkers? It's wrong, because this is forcing a current into the gate of this thing. I need a reference branch here. I need a mirror. I needed to do it that way. But now it works. So now this current is proportional to the temperature, and GM is inversely proportional to temperature, so they cancel each other out. Also, my gain is really dictated by the ratio of this resistor to this resistor, which is that resistor. So now we've defined a gain that's defined as the ratio of these two resistors. So you ideally want these two resistors to be of the same kind or different kinds if you want to get low temperature dependence. Same kind, because now you have two resistors whose ratios determine the temperature dependence, the gain, and if they have the same temperature dependence, the temperature dependence to first order cancels. Does that make sense? Right. Okay, I know I threw a lot at you today, so that's fine. We will build upon this. We'll kind of work on these things, and we'll build up on these things and make it more. We will reuse these concepts and revisit them as we go. Okay? Any questions?